title of my talk is Foot Placement-Based Angular Momentum Dumping for Running. In running, if we'll have a look at one stance phase. So, 2, 3. Starting with a foot position. Foot. That's the one. And an initial set of mass position.
Excuse me? Writing a larger font.
If you could take shifts, by the way.
Oh, we should be here. We can train for this.
And an initial velocity. Imagine a basically arbitrary force pointing from the foot to the center of mass. That's how non-arbitrary it is, because it's constrained to point always towards the center of mass. You have a force distribution F of t, which might be pointing up like this. It's moving like from here to there, while the center of mass is being modulated through it. You end up at a terminal position xt and a terminal velocity x dot t. Now, since I said the force is always pointing from the foot to the center of mass, we have tau, or I put it here, tau center of mass over time equals 0. 0 for ish. Or BSD-ish, if you have a point. Anyway, so where's the 12? I'm looking for this thing.
What's tau?
It's torque. The torque around the center of mass is 0. Look at the and there we go. Okay. Now, like, if you want to compute the change in linear momentum, delta L, it is some function of the robot's mass. Can you lift it higher? The robot's terminal velocity. A bit lower. A bit lower, please. The terminal velocity and the initial velocity. And it's also directly proportional, like, to the mean force acting like this. Mean force times the stance time.
Johannes, your handwriting is terrible. Why don't you hold the pen still and have...
Anyway, so what I say is the change in linear momentum is a function of like the takeoff velocity, impact velocity, touchdown velocity, and mass. And it can also be it's directly proportional to the mean force times 2 minutes. Okay. Okay. Now imagine you put your foot instead of here, while your touchdown position is still here, the trajectory is still the same. Your force profile simply shifted over. So now you have a new foot position. So your foot is moving by some delta t. And this is now just a vertical foot position. Through this, you still have the force profile. We're looking at that. Now the torque about the center of mass is simply P cross this F over T. And now the change in angular momentum, a bit higher please. The change in angular momentum, yeah, perfect. Is an integral over this tau of center of mass of T times T. And it can also be expressed as delta P, 1 minute, thank you, delta P cross delta L. So there's a connection between this change in position versus this change in linear momentum. now you can reformulate, like if you're now looking for some step adjustment, this delta P is a function of the change in linear momentum, which for some reason, for example in the BLT controller, you might know beforehand, and take it as a constraint basically, and some desired change in angular momentum. Right, so you have a change, like the actual change in angular momentum is a function of this P cross delta L. You can basically invert, and actually you cannot invert because it's a cross product. However, it's two-dimensional. Thank you very much. What is it? If you imply the constraint that only the effect of this delta that's not pointing along the force has an effect, it's a 2x2 problem. So you can find anyway a horizontal, for example, foot placement adjustment. That is the best for your angular momentum dumping task. In some cases, in many cases, you may be building up angular momentum, and may want to like dump it out. So, for example, when running, maybe you have like building up angular momentum backwards, and you want to like dump it over the steps. No time for questions. I'm looking forward to more questions during, I don't know, maybe the lunch on the mountain. Thank you very much.